SwayamPrabha. Digital India. Educated India.
Welcome to this NPTEL course on Fundamentals of Theoretical and Experimental Aerodynamics. In the first lecture, we are going to have an introduction on aerodynamics. We are going to look at its relevance and applications. Let us see what are the concepts which we are going to cover in this lecture. We are going to look at definition of aerodynamics. We are going to look at approaches that we take during an aerodynamic study. We are going to look at relevance and objectives of an aerodynamic study and also applications of aerodynamics. The key points that we are going to cover during this lecture include airflow, aircraft, forces and moments which act on an aircraft, the different approaches comprising of experimental, theoretical and computational approaches, at least their definition, and little bit on wind tunnels which are used for experimental studies in aerodynamics. Let us look at definition of aerodynamics. So, when we try to define the area, we say that the subject aerodynamics relates to the study of flow of air past an object of interest, which is often an aircraft, a craft which can fly in air. We may be interested with also flow of air past other objects like trains, automobiles, buildings, wind turbines and many other objects of interest which come under the purview of aerodynamic studies. Aerodynamics incidentally is an important branch of aerospace engineering. When we say aerodynamics, we are talking about dynamics of air, that means moving air. The term air is used in a generic sense. It basically means the flowing gaseous medium, which could be air, which we see in our atmosphere, helium, hydrogen and many other gases depending on the application domain that we are looking at. An aircraft is a body which is able to fly because of aerodynamic forces and moments which are generated by the action of air flowing past it. So, when air flows past an aircraft, there is a pressure distribution which develops around the aircraft. There is also a distribution of shear stress which develops on that surface, and then when these act in an integrated manner over the entire surface, there are generation of forces and moments. These aspects will be studied in more detail in later lectures. Now, the flow of air can occur during the flight of an aircraft through the atmosphere. The forces and moments which are produced through the pressure distribution and skin friction acting on the surface of the body are a major area of interest while we study aerodynamics. While designing an aircraft, motion of air flow past a scaled down model of the aircraft is often studied in the test section of a wind tunnel. There are different kinds of wind tunnels which are used in aerodynamic studies depending on speed of airflow primarily. This helps to assess the forces which would occur finally on the actual aircraft. So, the testing is done on a much smaller model, a scaled down model, but the results which come out of such a test are scaled up for the actual aircraft or the prototype. Aircrafts are most often much heavier than air, but can still remain afloat while flying in air because they generate adequate aerodynamic forces and moments which keep them flying. Development of such vehicles helped achieve human flight in the atmosphere. Let us briefly look at the approaches that we take for performing an aerodynamic study. We see on top the first point saying that there are three major components or approaches that are taken in modern aerodynamic studies. Number one, theoretical, which includes analytical and semi-analytical means. Number two is experimental, where we make use of wind tunnels and other experimental facilities. And number three, numerical computation, which in modern day parlance is called as computational fluid dynamics or computational aerodynamics. The different approaches are often meant to complement each other and also validate each other while we study an aerodynamic problem. Each approach has its own advantages as well as disadvantages. Usually, if possible, the most effective approach is to amalgamate both experimental as well as either theoretical or CFD investigation in a viable manner to solve a practical aerodynamic problem. Let us look at the theoretical solution in some more detail. So, when we seek theoretical solution, we are looking at exact or analytical solution of some governing equations. Most often they are certain conservation equations which represent the flow field, which is of interest as far as that aerodynamic study is involved. Often for seeking exact or analytical solution, we have to make some simplifications. Most often we see that there is a simplification in the domain geometry, or there is a simplification of the body geometry that we are trying to model. There are assumptions which are made which do not always very well cater to all kinds of real world situations. Due to these assumptions, the solutions thus generated have to be carefully applied to analyze a flow problem. So, we are finding that there are issues where we have to carefully handle how we take the solution forward. So, if you are making assumptions, you have to be clear that what impact those assumptions will have on the solution that we are generating. That is why we have to be very careful when we apply the solution to analyze the flow problem. For example, if you have used governing equations which are meant for a flow field which is inviscid, that means it is devoid of viscosity, then we cannot expect that it will do well for a situation where the flow is primarily dependent on the viscous behavior. So, this is where the assumptions that we make have a profound impact on the solution. A comparison with experiments or numerical simulations which try to replicate the actual problem, that means the real world problem that we are trying to solve, would reveal the range over which the theoretical solution is satisfactory. This is where complementing the different approaches comes into play. So, we bring in multiple approaches and we try to compare the outcomes and then finally come to a conclusion that what the actual solution should be looking like and where are the limitations of a theoretical solution. So, that basically identifies that over what range the theoretical solution is doing satisfactorily. We have cited a few examples here where a theoretical solution is possible, not that all problems come under the purview of a theoretical solution. That means you may not be able to solve every problem that you see around yourself, which categorizes as an aerodynamic problem of interest using theoretical solution means. So, you can seek theoretical solution for some of these problems. The first example is Laplace equation. We will see later. It is represented by an equation of this kind: Laplacian phi is equal to 0. Phi is a dependent variable, and this is of course a vector calculus operator. Now, it solves potential flow over a cylinder or an airfoil. Airfoil is nothing but a section of a wing. Therefore, it is of enormous importance in aerodynamics because it is a streamlined body. It has very little drag force and it has the capability of generating large lift forces. Therefore, it is called as a streamlined body. We will look at more on drag and lift and nature of streamlined bodies in the upcoming lectures. Next, solution of linear wave equation. So, that deals with propagation of sound waves or acoustic waves. That also has a theoretical solution. Blasius solution of boundary layer deals with incompressible boundary layer on different geometries. Starting from flat plate, you can extend the solution to other geometries also. Different exact solutions of Navier-Stokes equations. Two of them are Couette flow and Hagen-Poiseuille flow. So, these are some of the examples where a theoretical solution is possible. But beyond this, there are a large number of real life problems which cannot be simplified to an extent where theoretical solution is available. Let us next look at the experimental approach. In this slide, you can see a couple of pictures which are associated with wind tunnels. Experimental studies in aerodynamics are performed using wind tunnels. Wind tunnels are meant for studies to be conducted at different speeds. Some tunnels may help you to conduct experiments at subsonic speeds, some at supersonic or even hypersonic speeds. The one that you see over here is for low speed testing, that means subsonic testing. It can create a test section velocity of the order of about 30 meters per second. The heart of a wind tunnel is its test section. So, let us see where the test section lies. In this picture, you see an opening through which the air gets into the tunnel. Why? Because there is a fan running at the other end of the wind tunnel, which creates suction, and therefore, the air is sucked into the tunnel through this inlet. It is then accelerated and then sent into the so called heart of the tunnel, which is called as the test section. We call this as the test section. From the name itself, it is evident that that is where we would like to place our models for wind tunnel testing. Now, this is a closer look at the test section. So, you can find that there are windows through which there is optical access, and there are different instruments which are kept around the test section, which are used for making certain measurements. So, in the test section, we are going to perform aerodynamic measurements on scaled down models of prototypes. Because there are some dimensional constraints, we cannot make the test section very large because of certain constraints. We have to make the models small enough so that they can be accommodated into the test section, and you can also make the measurements using suitable measurement tools. You may be interested in measuring pressure on the surface of the model. You may be interested in finding out what forces and moments are acting on the model when there is airflow. You may be interested to look at how the velocity behaves behind the body after the flow has crossed the body, which is called as the wake. So, you are going to survey the wake of the body. You may be interested in visualizing the flow around the body as the air moves past it. So, you may be able to use certain tools which make the flow visible to you, and that is very, very interesting. Some of the pictures that you see over here relate to that. We will come to that soon. You should also have appropriate model positioning system, that means by which you hold the model in place within the test section, and of course, appropriate measurement instrumentation. This is a means of visualizing the flow as it moves through the test section. So, this is what is called as smoke flow visualization. You create a smoke stream, individual smoke lines which move past the model and gives you a feel of how the flow is behaving as it moves past the model. In the second picture from the top, you see the same model illuminated using a laser sheet, and what you may not be able to see is that this flow is seeded with a very large number of very small sized particles which are carried by the air as the air moves past the model. So, these small particles are also advected along with the air, and they take up the profile of the body as they move past the body. If you track those particles suitably, you should be able to get the velocity vectors. This forms a part of a measurement technique which is called as particle image velocimetry. We will talk about it in much more detail later on. Let us look at the numerical solution, the approach of numerical solution. Here we solve the governing equations of fluid flow using the relevant partial differential equations. So, we are interested in solving the governing equations of fluid flow, which are basically partial differential equations. How do we solve them? We do not solve them analytically, generating exact solutions, but rather we approximate them. We do not solve them exactly, but we solve them in an approximate manner, but we ensure that the errors are kept to the very minimum, so that you get a solution as good as an exact, if an exact solution really existed. Thereby what you end up creating is visualization of the flow by numerical means. So, earlier you saw visualization of the actual flow by using experimental means. So, those were physical experiments, these are numerical experiments. You can see a similar airfoil section here, and you can see certain flow features which are created around the airfoil as the angle at which it is inclined to the airflow changes. So, you can imagine that there is some angle that this airfoil section is making with the incoming airflow. That angle is often called as the angle of attack. So, as you change the angle of attack, you are increasing it, as you see the pictures in the lower part, and you find that the flow looks very, very different as the angle of attack increases. Here you find other contours plotted which give you information about the flow field. This is showing you the pressure distribution about the airfoil at different angles of attack. So, these are different kinds of analysis that you can do when you are seeking a numerical solution. What is the relevance and what are the objectives of an aerodynamic study? There are many. We have just jotted down a few here. So, you are interested to study the flow physics in a big way, for which you look at the way the flow behaves around the body through velocity distribution, around the body and in its wake. That means, once the flow has left the body and has gone downstream. You quantify the aerodynamic forces and moments which act on the body. You try optimizing the shape and also sizing the aerodynamic body to generate desirable flow features and also generate appropriate aerodynamic forces and moments. You may like to maximize the lift to drag ratio. So, lift is a kind of a penalty, and we may say that lift is a kind of a benefit while drag is a penalty, and therefore, you may say that lift is on the credit side and drag is on the debit side of the aerodynamic balance sheet. You may like to maximize the lift to drag ratio to maximize the aerodynamic efficiency of the configuration. You use the aerodynamic surfaces to generate adequate forces and moments to maneuver the aircraft. So, you may need to know whether the surfaces are correctly scaled, correctly sized. You may like to study the aerodynamic effect of the atmospheric disturbances like turbulence and gust, study the deformation of flexible aerospace structures under aerodynamic and inertial loads, and for very high speed configurations like rockets and re-entry modules or capsules, you will be interested to learn about aerodynamic heating and how you would like to design your heat shields to protect these bodies. These enormous heatings are produced due to the high velocities at which these vehicles travel. There are shock waves and very high viscous dissipation in the boundary layer, about which we will discuss later in some lectures. So, aerodynamic heating is a major issue at high speeds. That is all that we need to understand at this point. High speeds can make the flow chemically react, and the extremely high temperature conditions produced on rockets and re-entry vehicles lead to chemically reacting flow, which also has to be taken into account. Therefore, we realized that there are enormous number of objectives that we may be looking at. That kind of outlines the relevance of an aerodynamic study. Let us look at a few applications. There are myriad, but we would like to look at some of the most important ones. Aircrafts could be of different kinds. They can have fixed wings, they can have rotary wings. For example, this is a helicopter model which has rotary wing. So, the wings rotate, generating the aerodynamic forces and moments. This is a defense aircraft used for military applications with a fixed wing. This is a passenger aircraft with fixed wing. So, these are some of the aircraft configurations, and we do a lot of aerodynamic studies to understand their behavior and to design them appropriately. As far as spacecraft aerodynamics is concerned, we are only concerned about the portion of their travel through the atmosphere. So, atmospheric flight occurs during ascent of a rocket or re-entry of a re-entry capsule into the Earth's atmosphere. You may be interested to also look at space probes which are entering atmospheres of other planets as well. So, that involves spacecraft aerodynamics. You see a rocket lifting off from almost zero velocity, and it would be reaching extremely high velocities by the time it reaches the outer reaches of our atmosphere. So, all through the ascent, we look at its aerodynamic behavior. This is a picture of a re-entry module which has safely re-entered the Earth's atmosphere and is going to touch down soon on the Earth's surface. For its protection, it is being tied to few parachutes so that you can control the descent rate. You can think about fixed rotary and flapping wing micro air vehicles, which are vehicles of very small size, and unmanned air vehicles for different purposes, starting from defense applications to reconnaissance and so on. So, as you can see, this is a very small flying vehicle, handheld. This would typically qualify as a micro air vehicle. The other one could qualify as an unmanned air vehicle, or in brief UAV, and the micro air vehicle in brief MAV. We are interested in aerodynamics of ground based vehicles, automobiles, the usual ones, the racing cars, which are the high speed ones, buses, trucks, high speed trains, and many other vehicles that we see on roads and moving on the earth's surface. Aerodynamics of ground based structures, which see a lot of wind loading. So, that falls in the domain of wind engineering and has to deal with airflow past earth fixed structures. You can have high rise buildings, towers, chimneys, which fall in the category of tall slender bodies encountering enormous aerodynamic loads. There could be bridges, there could be very large wind turbines as well. Now, the structure of these earth fixed structures could be flexible and they could be responding to the airflow and undergoing deformation. One thing that we have to be very careful about, that they do not get into a very damaging oscillatory mode while the wind moves past them, because there is vortex shedding which occurs from many of these surfaces, and that is basically going to lead to some kind of a oscillatory load on these structures, and they can set these structures to a very dangerous mode of oscillation if the frequencies are close to the resonant state. There is a domain of sports aerodynamics which is becoming increasingly popular. You can see a cyclist cycling on a fixed cycle model placed in a wind tunnel, and the flow field is being studied using smoke. So, the posture, the position of the cyclist, etc., and the cyclist's attire, outfits would have to be optimized to reduce the drag acting on the cyclist and therefore optimize the performance of the cyclist. Skiers are also studied under sports aerodynamics. We study aerodynamics of balls, footballs, cricket balls, golf balls, and so on. We also study aerodynamics of birds and insects, which fall under the category of natural flyers. So, there are myriad applications of aerodynamics, and the applications keep growing with time. Looking briefly at the references which you might follow for this course: Fundamentals of Aerodynamics by J.D. Anderson Jr., Introduction to Flight by the same author, Low Speed Wind Tunnel Testing by Barlow and other authors, a first course in aerodynamics authored by me. So, these could be some of the useful references for this course. Before we finish, we would like to conclude by saying that in this first lecture, we discussed about the definition of aerodynamics, the approaches taken to perform aerodynamic studies, relevance and objectives of an aerodynamic study, and the enormous number of applications of aerodynamics. We would like to elaborate on many of these aspects in the later lectures. Thank you.